Everyone, this is lecture 2, part 2. So we're talking about the chemistry of life, and this part 2 is going to focus on water and life, and then hopefully we could just keep this 2 parts. So water and life, in the Campbell biology textbook, this is chapter 3. In OpenStax, this is chapter 2, section 2. So water is super important, right? Not just for aquatic animals, but even terrestrial animals. So water is really fascinating, actually. We kind of take it for granted that, yeah, water is important for you, but there's a lot of things that make it so important to life. And part of that is just because of its chemistry, like the way that its molecules happen to be have different properties that enable life to happen. So one of the key properties about water molecules is that water is a polar molecule. So if you remember from lecture 2, part 1, a polar molecule has a part that is partially negatively charged and other parts that are partially positive charged. So a polar molecule has those, regions of different partial charges. And so water as a molecule has this because of the electronegativity of oxygen and how it kind of hogs electrons. So the electrons of these polar covalent bonds spend more time near the oxygen than the hydrogen, and that's what gives it the partial negative charge. And so this affects how water molecules interact with each other and then also other things. So in a water molecule, because the overall charge is unevenly distributed, there's polarity, and this polarity lets water molecules form hydrogen bonds with each other. So remember hydrogen bonds between a hydrogen that is partially positively charged and another molecule that is partially negatively charged. So those are hydrogen bonds that are possible because water is covalent, so they can bond with each other in that way. And so that was just kind of a reminder about some of the basic chemistry. And so 4 of water's properties that facilitate an environment for life are cohesive behavior, its ability to moderate temperature, its ability to expand upon freezing, and its versatility as a solvent. So out of context, this might not make much sense yet, but on each of the, on the following slides, I'll talk about each one of these properties. So number 1, cohesion, that it has cohesive behavior. So these hydrogen bonds between water molecules can help hold these water molecules together. And this is a phenomenon called cohesion. So each of the water molecules kind of like holding on to each other is cohesion. And cohesion can result in high surface tension. So surface tension is a measure of how difficult it is to stretch or break the surface of a liquid. So because there's all these water molecules bonded together through hydrogen bonds, there's surface tension, and that's why some organisms, like the spider, for example, are able to like walk on water because they happen to not be able to disrupt those hydrogen bonds. And so that leads to high surface tension. So you can't even get like a cup of water and put like a sewing needle and drop it very gently on the surface. And again, hopefully you're not like dropping it in force, but if you were to drop it very gently on the surface, it could stay on the surface because it isn't breaking that surface tension. And cohesion is actually pretty important because it helps transport water and the dissolved nutrients in the water against gravity in plants. So if we look at this picture of a tree on the right, there's water that comes up the roots, and then it has to get to all these leaves of the tree somehow. And so water is able to be pulled up the tree against gravity. And then as evaporation happens, from all the leaves and things like that, it kind of helps pull water upward. And so cohesion is the water molecules kind of like pulling each other up. So it's these attractions between water molecules. And then there's also this phenomenon called adhesion, and adhesion is an attraction between different substances. So in this case, the water molecules and the plant cell walls. So cohesion is between similar things, between water. Adhesion is between one thing and a different thing, so water and the cell walls. So there are kinds of like water conducting cells in plants, and so that adhesion with the water being able to kind of like be attracted to these walls is also part of what helps it get pulled up. So these two forces, cohesion and adhesion, help draw the water up against gravity to all the different, leaves and cells. Property number 2 of water is its ability to moderate temperature. So water absorbs heat from warmer air and releases stored heat to the cooler air. And this is really helpful, as some of us might know, in the summers. So water absorbs heat and then is able to kind of release heat. And so that's really helpful to living things. Water can absorb or release a large amount of heat with only a slight change in its own temperature. So there's some more concepts from chemistry that we didn't really cover yet from last lecture. But there are different kinds of energy. And so kinetic energy is the energy of motion. And there's kinetic energy associated with random motion of atoms or molecules, and that's called thermal energy. And so temperature is or represents the average kinetic energy of molecules in a body of matter. And when thermal energy is able to transfer from one body of matter to another, this is defined as heat. And so we can measure energy in calories, and this might sound familiar. So a calorie is the amount of heat that is required to raise the temperature of 1 gram of water by 1 degree Celsius. So it's like how much energy and heat that you have to put in for 1 gram of water to increase in temperature by 1 degree Celsius. And kind of flip-flopped, it's also the amount of heat released when 1 gram of water cools by 1 degree Celsius. So calories are a measure of energy. And so if that sounds familiar, if you've seen calories on food packages, those are a measure of calories. But in food, there's usually a lot of energy and stuff. And so when you see stuff on food labels, you might notice that the C in calories is actually capitalized. That's because food calories are actually in kilocalories. So 1 calorie is like, 1 calorie. If you add the prefix kilo to something, that usually means there's 1,000 of that base unit. So 1 kilocalorie is 1,000 calories. And so in like food and nutrition science, they kind of just give this as like a given when they say capital C calories, because usually it's measured in kilocalories. And I guess they just wanted to shorten it. They didn't want to confuse people. I don't know. But yeah, so calories as a base unit are usually lowercase. On food packages, if you see it, it's actually a capital C calories, indicating it's kilocalories. So it's kind of a fun fact. So the specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So it's kind of like how the calorie is measuring how much heat is required for water. But a specific heat is for anything else. So if you're measuring coffee, the specific heat of this coffee would be how much heat has to be absorbed for 1 gram of that coffee to change its temperature by 1 degree. And so, yeah, that might be different than like water. or soda or something else. So the specific heat of water is 1 calorie per gram over degrees, well, 1 calorie over grams per degree Celsius, which makes sense because the calorie is literally defined as like water. So anyway, water has a specific heat, and so water resists changing its temperature because of its high specific heat. Like it actually takes more energy to change temperature compared to other stuff. Hopefully that makes sense. And water's high specific heat can be traced to those hydrogen bonds. So heat is absorbed when those hydrogen bonds break, and then heat is released when the hydrogen bonds form. And so the fact that water can do these hydrogen bonds all the time helps it really like moderate its temperature changes. And yeah, that's really helpful because that high specific heat of water minimizes temperature fluctuations to within limits that allow life to happen. So for example, especially if you think about like the temperature when you go to the beach compared to somewhere like inland, a large body of water can absorb and store a huge amount of heat from the sun during the daytime, and then during summer while warming up only a few degrees. So say for example, the ambient temperatures, it's pretty hot, but when you go closer to a body of water, it's not that the temperature happens to be cooler there, it's that the water, that big body of water is absorbing all that heat. And so that's why it feels cooler, because all that heat is going into the water bonds. Does that make sense? So a large body of water can absorb and store a huge amount of heat from the sun in the daytime, while only warming up a few degrees. So it's not like this water is now going to be boiling when you get in. It's absorbing all this heat, but it's not actually changing that much itself, which is pretty cool. And so at night and during the winter, that water can also kind of release energy and warm up the air. So it's not as cold as drastically because it's releasing that stored energy. So this helps moderate air temperature in coastal areas. So for example, you don't usually see it snow on the beach, right? Because the water is kind of helping release energy and keep it from getting the ambient temperature too low. So here's a picture showing that, for example. So these are temperatures on an August day here in Southern California. So around us in like San Bernardino, the high desert, it's going to be about 100 degrees or maybe more. But if you were to go closer to the coast, again, it's all that water that's absorbing the heat. And so the temperature around here is only going to feel like 75 degrees or maybe even like 72 degrees. And then if you were on the water, it'd be like 68 degrees. So again, it's not just that like it is only that it's hotter more inland. That same kind of energy is still radiating over here from the sun, but that energy is getting absorbed and like held and stored in the body of water. So it feels like less. And so when heat is absorbed into water, there can be evaporation. So evaporation is transformation of a substance from the liquid to gas. So water can be liquid, and then if there's enough heat applied, it can evaporate into the gas form. So heat of vaporization is the heat that that liquid must absorb to then be converted into gas. And so that is also kind of helpful for us. So as liquid evaporates, its remaining surface cools. And so this is called evaporative cooling. So that's also useful for us because we sweat, right? Like mammals sweat. So when you produce sweat, water kind of forms, and then when it evaporates off of your skin, it's taking some heat with it. So then the remaining surface feels cooler, and that evaporative cooling helps regulate our temperatures, right? So evaporative cooling of water also helps stabilize temperatures in organisms and in bodies of water. So here's an example of like an elephant trying to cool itself down, spraying water on itself, because then the water molecules can evaporate and take some of that energy with it. Okay, so property 3 of water is that it can expand upon freezing. So other stuff, if you froze it, it becomes more dense. But water is unique in that when you freeze it, it becomes less dense than a liquid. It's lighter as a solid than it is as a liquid. It's because at 0 degrees Celsius, water molecules get locked into this kind of pattern, a crystal lattice. So just from the like physics basically of how the water molecules orient and face each other, it forms this kind of like pattern. And that's what makes it less dense when it freezes. So those hydrogen bonds keep the molecules far enough apart to make the ice less dense than liquid water, and actually about 10% less dense than liquid water. Which is helpful. We might think like, okay, who cares? My ice in my cup of water floats instead of sinks. But in a big picture sense, if ice sank, then all bodies of water would just freeze solid, making life impossible on Earth. So the fact that water, when it freezes, kind of stays at the top can help other things stay below and not be frozen solid. And then characteristic number 4, which is kind of like the big one for our course, because this property of water is going to happen to come up a lot, is how it's versatile as a solvent. Like it can be a solvent for a lot of different things. And so what does that mean? What's a solvent? So a solution is a liquid that is a completely even mixture of substances. A solvent is what you're dissolving something in. And then the solute is the substance that's being dissolved. And so a good example is like iced tea or powdered lemonade or something like that. So the powdered lemonade, for example, just, or salt or whatever, is the solute. That's the thing that you're going to dissolve in water, and the water is going to be the solvent. So when you're making a cup of like salt water or lemonade or powdered iced tea, you're making a solution. After you have it mixed evenly, it's a solution because you're mixing 2 different substances. So water is typically a solvent for a lot of different things, especially in your body. And I mean, you could have other things. So for example, like your creamer in your coffee, the creamer in that case is the solute, and then the solvent is the coffee. You can mix something and something else, and that is a, solution. But to be specific, an aqueous solution is one that's telling you that water is the solvent. So a lot of your body, your cells and your tissue fluids are aqueous solutions, meaning it's like stuff dissolved in water, not dissolved in other stuff. I think this figure is cutting off some text, but basically that's what it's saying too, is that most chemical reactions in organisms involve solutes dissolved in water. And again, because water is polar, that's what allows it to be such a good solvent. So because water is polar and it has parts of the molecules that are positively charged, they can attract negatively charged things. And because there's other parts of water molecules that are negatively charged, they can be attracted to positively charged things. And so that's what helps dissolve so many different things in water. So especially if something is ionic, and it has a charge, like salt, so sodium and chloride, they get surrounded by these water molecules, and then that's how they are able to like dissolve. And water is cool because it's not just polar stuff that it can dissolve. Water can also dissolve compounds made of non-ionic polar molecules. And even large polar molecules like proteins. So next week we'll talk more about big molecules like proteins. But even large polar molecules like proteins can dissolve in water if they have parts of them that are ionic and polar. So even this huge molecule, it's not getting like surrounded by just a few. It can be surrounded by a bunch of water molecules, because they're going to be attracted to the parts that are negatively charged or positively charged. So yeah, water can dissolve a bunch of stuff. And substances can have different affinity for water. So some stuff likes water, some does not. If something is hydrophilic, then it likes water and it will dissolve in water. If something is hydrophobic, it does not like water and will not dissolve evenly, if at all, in water. So salt is definitely hydrophilic. It'll dissolve in water really well, right? Some stuff like oil is super hydrophobic. You might have had that or seen that experiment for kids where you have like a water bottle and then you put water and vegetable oil or something, and then you try to mix it and try to mix it and it never mixes. That's because of the way that the molecules do not want to interact, basically. So oil molecules are hydrophobic. They do not want to interact with water. They won't ever mix with water. They'll always separate as many times as you shake that water bottle. So hydrophobic molecules that are related to oils actually make sense that they're the major ingredients of cell membranes. So when you picture a cell, it might be in like a circle. The cell membrane is what helps separate the inside of the cell from the outside of the cell. And so it kind of makes sense that if most of the inside of the cell is watery, most of the outside of the cell is watery, there would be a boundary that does not like water, and that's what keeps them separated. So again, most chemical reactions in organisms involve solutes dissolved in water. And we can measure the mass and the number of solute molecules in a solution, in an aqueous solution. So again, that is telling you that it's dissolved in water. So this is going to be, it's definitely relevant to biology. You're going to get this a lot more in a chemistry course. But it's still important to talk about, especially if one day you want to go into research, or if you do want to go in the health field, you're going to have to know, some chemistry like molarity and things like that. So just to cover it quickly, the molecular mass is the sum of all masses of all atoms in a molecule. So in a molecule, you can have more than one kind of atom, remember? So like H2O, there's 2 hydrogen atoms and an oxygen atom. So the molecular mass would be the mass of all those atoms in that molecule of water. And then we can measure the number of molecules in these units called moles. And so if you remember Avogadro's number, so 1 mole is a unit. So kind of like a dozen is 12. They came up with this word to say 1 mole is 6.02 times 10 to the 23 molecules. So it's like a lot of molecules. That's why they wanted to divide it into a smaller unit. So 1 mole is 6.02 times 10 to the 23 molecules. So then it's easier to say, oh, there's this many moles there. And yeah, so Avogadro's number and the unit Dalton were defined such that 6.02 times 10 to the 23 Daltons is 1 gram. So those are kind of just different measurements of the mass of a molecule. And then molarity is the number of moles in an amount or in a volume of the solution. So molarity is the number of moles per liter of a solution. So liter is a volume measurement of a solution. So it's kind of trying to say like how many of these molecules are there in this amount of water or whatever solution. Yeah, then that's kind of it. Again, you'll get more in chemistry for sure. And so another aspect of water, and that we have to consider because a lot of things are dissolved in water, is how water molecules can kind of vary a little bit. So sometimes two water molecules will interact and transfer a hydrogen atom. So let me show you right now here. So on the left are two figures or two molecules of water. Sometimes, yeah, they can interact and then one of them gains a hydrogen atom and then the other one loses it. And then so this ends up with a molecule that's 3 hydrogens and 1 oxygen, hydronium ion. And the other one is going to have 1 oxygen and 1 hydrogen, a hydroxide ion. So sometimes just naturally that can happen. It's not very common, but it can happen. So one molecule is then a hydronium ion, H3O, but we usually kind of just simplify it as H+, and then the other one is OH-. And water is in a state of dynamic equilibrium. So this might happen, but it'll be at the same rate that is reformed. So it's kind of like a neutral reaction that goes back and forth and doesn't really end up making an effect in like a pure water solution. Well, pure water. Though statistically rare, that doesn't, yeah, it's typically equilibrium at equilibrium. If they happen to dissociate, that could lead to a great effect on organisms because those ions are very reactive. H plus and OH minus, they're very reactive and they can kind of like cause big changes in cells. So changes in their concentrations can drastically affect the chemistry of a cell. So in pure water, that reaction might be happening, but the concentrations of the H plus and the OH minus are always going to be equal to each other. And then again, they're going to maybe like go back to water and, it'll be at equilibrium. But if you add something else, sometimes that will really change those concentrations of the hydrogen ions or hydroxide ions. So adding certain solutes can change the concentrations of the hydrogen and hydroxide ions. And we would call these solutes acids or bases, depending on which one they alter. So biologists use the pH scale to describe whether a solution is acidic or basic. Well, chemists do this too, but especially in biology, this is, something that we focus on. So acids increase the hydrogen ion concentration of a solution, and bases end up reducing the hydrogen ion concentration. And strong acids and bases dissociate completely in water, whereas weak acids and bases can reversibly release and accept hydrogen ions. They still shift the balance of those two ions away from neutral, but it kind of like reversibly does it. Versus strong acids and bases really like drastically alter them. So the pH scale is a measure of those hydrogen ions. So the pH of a solution is defined by the negative logarithm of the concentration of hydrogen ions. So the hydrogen ions, you would do the log, but you would actually do the negative log. And this is, you don't really need to know that much about the specifics of how the pH scale works for this class, but it's good to know the theory behind it. So it's based on how many hydrogen ions are in a solution. Yeah, and then it's the negative log. So usually in a neutral solution, the hydrogen ion concentration is going to be 10 to the negative 7. And by following this equation, that means the pH is 7. Because 10 to the 7, and then, yeah, it's a negative log. So even though it's 10 to the negative 7, that cancels out. So it ends up 7. So pH is 7 in a totally neutral aqueous solution. And if you add an acid or a base that changes that concentration, then that's going to change the pH. So acidic solutions have a pH of less than 7 degree or 7, and basic solutions have a pH greater than 7. And at first that might sound counterintuitive because if something's acidic, doesn't it have more hydrogen ions? That's true, but remember this is the negative log of that. So even though the hydrogen ion concentration is getting higher, it's going to lower the pH just because of how the equation is. So pH below 7 is acidic, pH above 7 is basic. Most biological fluids have a pH in the range of 6 to 8, but it depends on like what the solution is, what it's doing. Stomach acid is super acidic, but your blood should be pretty neutral. Yeah. So that's like the fundamentals of the pH scale. And here are some examples for context. So 7, again, just pure water should be around 7. Human blood is pretty close to 7. It's like 7.35. If we wanted to see examples of acidic solutions, then urine is pretty acidic. Coffee is pretty acidic. Tomato juice, lemon juice. So anything that will give me heartburn, pretty much. Which kind of makes sense because it's combining with your stomach acid, and which is also acidic and whatever. So yeah, acidic stuff is below pH 7. So sometimes the scale in an image will be flipped one way or another, but make sure you notice which side has the 0 and which one is the 14, because some figures will have it the opposite, but pay attention to the numbers. So pH below 7 is acidic, and then pH above 7 is basic. There's going to be less hydroxide or hydrogen ions. And so sometimes it makes sense if you have like heartburn or something, you could be taking milk of magnesia, which is basic, and kind of evens it out. So that kind of leads me to this idea. So buffers. The internal pH of most living cells should be close to 7. Is close to 7, and then you want to keep it as close to 7 as possible. Even a slight change in pH can be harmful. And so buffers are substances that help minimize these changes in concentrations of those ions. Most buffer solutions have both like a weak acid and its corresponding base. And then that way having those two forms of a molecule can help either accept or release hydrogen ions as needed. Yeah, so they combine reversibly with the hydrogen ions and then can kind of help buffer any changes. So here's an example of like a buffer of this I don't remember the name off the top of my head right now. But so this form of the molecule is a weak acid and can donate protons or hydrogen ions. And then this form is a hydrogen ion acceptor, so it can take on an extra hydrogen ion. And so by having both of these around, it kind of helps regulate the hydrogen ions floating around. Okay, so that was chapter 3, water. And so there was a lot of extra details in there, and that kind of helped give a framework for things as we move into the rest of the course. But these are the main ideas. So the main ideas are how polar covalent bonds in the water molecules result in hydrogen bonds. 4 emergent properties of water are important and contribute to Earth's suitability for life, and how acidic and basic conditions affect living organisms.